collègues, j'ai le grand plaisir aujourd'hui d'ouvrir les leçons Jacques-Louis 2026 et d'accueillir Wang, qui est professeur au Courant Institute à NYU et à l'IHES. Les travaux de Wang occupent une place exceptionnelle à l'interface de l'analyse harmonique, de la théorie géométrique de la mesure et de la géométrie d'incidence. Ils renouvellent profondément notre compréhension des problèmes majeurs autour de la restriction de Fourier, des phénomènes de découplage, des ensembles de Furstenberg et du problème de Kakeya. Son travail récent avec Joshua Hazal sur la conjecture de Kakeya en dimension 3 illustre cette puissance des idées géométriques en analyse, à partir de situations de configuration très concrètes, des familles de tubes, leurs incidences et leurs volumes, et en extraire des principes d'une grande profondeur. Ces leçons Jacques-Louis sont un lieu où nous souhaitons faire entendre de telles mathématiques capables de modifier durablement un paysage scientifique. Merci beaucoup, Wang, d'avoir accepté notre invitation. Nous sommes très heureux de t'écouter aujourd'hui pour cette première leçon intitulée Union of Tubes and Kakeya Sects. Hong, welcome. The floor is yours.
Okay. Well, thank you very much for the very kind introduction, and thank you very much for the invitation. It's a great honor. I'll be talking about union of tubes. This whole series of lectures is planned based on joint work with drug stuff. Start with small scale delta that's much smaller than 1. And delta 2, the object we're going to study is has length 1 and radius delta. So the question we want to study is the following. This blackboard T, this one means a set of delta tubes. And so this one means 1 tube, and then the blackboard version means a set of delta tubes. Let's say contained in the unit form in Rn. And the question we want to we use this notation UT to denote union of tubes in T. So the question is, how large is the union of tubes? So we give a minimum lower bound on the volume of union of tubes. So before we make any proof, we need to first add appropriate assumptions. For example, the set of delta tubes, we cannot just repeatedly putting all the delta tubes like in the same location. So we need the delta tubes to be distinct. So T1 and T2 are distinct. The fraction of T1 and T2 has volume less than half of 2. So that's the basic assumption. But under this assumption, what can we say about the volume of union of tubes? We still need to add more assumptions. For example, one of the reasons why we are interested in this question is because the Kakeya of conduction can be rephrased as a question about union of tubes, and it gives some assumption on the set of delta tubes. But later through the lectures, we'll see that we have to modify this assumption to find slightly more general one that works better for the proof. So let's first see what's the assumption that comes from the Kakeya set conjecture. Says if T consists of delta tubes in every delta separated direction. Then the union of tubes should be greater than so this absolutely greater than 0, there exists such that the following. So in every delta separated direction means the following. So in the we take on the unit sphere, we take a delta net and like each point has distance about delta to its neighbor. And for each of this direction, for every direction in the delta net, we can take one delta in this direction. And for the other direction, we can take one, but we can change the location as we wish. So that's the assumption. We call this assumption the Peckel assumption. So this is what we call the Peckel assumption on the set of delta tubes. And another thing to notice is that here we have delta to some positive power. The reason why this exists, well, you can also ask whether it's reasonable to ask, let's say, 1/log delta or something like that. That's a more refined question. But the reason why such a term that goes to 0 exists is because of the Vesikovich example. So he showed that there exists a set of tubes satisfying Peckel function. And the union of tubes has volume goes to roughly little of 1. That goes to 0 as delta goes to 0.
There's dimension encoded here,
This is any dimension.
but I mean, the constant has to depend on dimension, right?
Yes, so
Right, so you give yourself a delta separated set of points on the sphere.
Yeah.
And it's for every set like that, then.
for let's say for every direction you choose a tube in this direction. But the word every is not that important. So you can say for most of delta separated direction or for a fraction of delta separated direction, you take one tube in this direction. But then you have some freedom to choose the tube because you can choose it anywhere in this parallel collection. And that's the amount of freedom. So any other question?
Yes. Sorry, I don't understand what the epsilon is.
Yes, so the role of the epsilon is that, so let's say the easiest question, like the initial question could be like, whether this is greater or equal than some constant. Then this is false because of the Vesikovich example, because there exists a set of tubes such that the union of them has volume less than any small constant, as we choose delta goes to 0. Is this setup clear?
No, I understood.
Because just to say that it grows as any power.
No, but I mean, there is some epsilon in the beginning, but it does not appear anywhere.
Epsilon is here.
Yeah. It's definitely the epsilon.
Yes, sorry.
Okay, I saw that.
Delta to the epsilon. Yeah.
I seem to.
So basically, Vesikovich says that there exists a delta tube satisfying the Peckel set assumption such that the union of tubes could be very small as delta goes to 0. And this Kakea-set conjecture says the opposite. It should go to 0, like in an arbitrary slow power of delta. And why do we care about this Kakea-set conjecture? Is because when we study, for example, linear solution to Schrödinger equation, we say F is a solution to Schrödinger equation, then we can usually decompose F into sum over wave packets, and each wave packet live on this tubes, a rescale version of delta tubes. And the interesting case is when we have the tubes pointing in different direction, and then we need to understand. So this is where Fp lives. Fp essentially lives in the tube, and when we want to understand this solution to Schrödinger equation, we want to understand how the F add up together. So one important component is to understand the geometry of the union of tubes, whether they can overlap a lot or not. And if they can overlap at a lot at some places, that at this place there is a risk that this F could potentially blow up. And that is why we are interested in understanding the union of tubes problem. But that's of course not the whole story, and there are a lot of one should also try to understand this oscillation when we want to understand F. So now let's so this Kakea-set conjecture is a special case of our original problem. In fact, in order to try to understand the Kakea-set in higher dimensions, one should go back to the original, more general problem and think about it. So let's try to think what's the best possible bound can we get for the union of tubes. So since the tubes are contained in the unit ball, then that's possible. Since the tubes are contained in unit ball, then the union of tubes cannot be greater than, let's say, 1 up to some constant. And the best possible is also when the tubes are entirely disjoint, in which case it cannot be greater than the number of tubes. So this means the number times the volume of one tube. I use this tilde here to denote there's some constant C depending on epsilon n. So this is the best possible bound up to these epsilons. In fact, the more general question is, can we give a classification about or give some criteria about the union, about the set of tubes, such that we can have this best possible bound? So already for this kind of question, in order to come up with some criteria, let's first try to come up with some counterexamples, like some enemy examples, so that we know how to have the right assumption. So the first example is let W be W1 times Wn minus 1 times 1. That's a rectangular box. And all the Wi's are greater or equal than delta. Otherwise, it cannot contain any delta tube. Then let T be a maximum set of distinct, pairwise distinct delta tubes. contained in W. So the number of such tubes is roughly the volume of W divided by the volume of tube squared. So the reason is that we can have the volume of W divided by the volume of tube many delta separated directions. We can put the one tube in it. And in each direction, we still have this many parallel tubes we can put inside W. So altogether, the number of maximum set of distinct delta tubes is the volume of W divided by a volume of T squared. But the point is that once we plug in this example, the union of tubes, since they are all contained in W, so it's at most W, the volume of W. The volume of union of tubes is at most the volume of W. But if we put this term on to the right-hand side, it can be, since they are all contained in W, and if those Wi's are less than 1, so it cannot be really 1. The number of tubes times the volume of one tube is W, the volume of W over the volume of T times. So we compare these two terms. These are the same. And the difference is that it's for this example, the bound fail by this factor. So the volume of W divided by volume of T, which usually is greater much bigger because Wi's are bigger than delta. So this is a simple example that this bound fails. Are there any questions? Okay. The second example is, so this example holds in any dimensions. The second example is sophisticated. So it only holds in higher dimensions. The second example is, suppose sigma, let's say Q, is a root, let's say hypersurface. That Rhodes hypersurface means that the hypersurface contains a lot of lines. And let's say containing a k-dimensional set of elements. So the example one could have in mind is xy minus cw equals to 1. And this hypersurface contains three-dimensional set of lines. So n is equals to 4, k equals to 3. Then we take T to be delta T contained in delta neighborhood of Q intersects a unit ball. And now the number of such tubes is roughly delta to the minus 3. And in particular for this example, we know that the union of tubes since they are all contained in the delta neighborhood of this hypersurface, is at most is roughly delta. And for this example, we know that the union of tubes has volume delta, but the number of tubes times the volume of one tube, because we are in R4, is roughly 1. And again, so this example fails on the best possible bound. And that we can see that this example happens in R4, and one can cook up similar examples in higher dimensions. So those are the two types of enemy examples that people have found in RN. For this lectures, we only have to deal with the first type of enemy examples. And in fact, our main theorem could be summarized as in dimension 2 and 3, these are the only type of enemy examples. But for higher dimensions, we don't have to worry about this type of enemy examples. Are there any questions? So, looking at those enemy examples, we need to come up with some assumptions such that we have there is a chance that we could obtain that lower bound. So, we could make the following definition: is the for any set W in Rn. The T bracket W just means the set of tubes containing W. And the it's natural to define the density of tubes containing W as delta TW as the number of tubes contained in W times the volume of one tube times the volume divided by the volume of W. And why it is natural to define the density, as we can see that for those enemy example. So what is the density of tubes in this one? That is precisely the number of tubes times the volume of one tube divided by W. So that is the volume of W over the volume of T. And we can see that for this example, the density is much bigger than 1 if the Wi's are much bigger than delta. And if you write this as W, then what is the density of tubes here? This is this quantity is 1 and is okay, this quantity is delta to the minus T times plus n minus 1 divided by the volume W, that is delta to the minus 1. So that is delta to the minus that's delta to the K plus n minus 2. So in our particular example, this density is to the minus 1, which is also way bigger than 1. But for this, it depends on K. It could be less than 1 for the density of tubes in W. But for the two enemy type, they are much bigger than 1. So also we can see that if a set of tubes has density in certain, if a set of tubes is contained in W and if the density is much bigger than 1, then this cannot possibly hold. So that's a special definition, and such definition first appeared in Wang's paper on the X-ray estimate of gases. Based on So we want to make some definition to say that the density of tubes in any set W is, or in any set W is less than 1. But as we said previously, fortunately in 3-dimensional space or in 2-dimensional space, the relevant W are convex sets. So we don't really have any let's say, and we don't have any proof before we made our definitions that the W has to be convex sets. But fortunately, in 2 and 3 dimensions, the convex sets happen to be enough, so it's simpler to estimate. So for simplicity, let's say that suppose a set of tubes T is a set of tubes contained in the unit form. Then we say that T satisfies that's convex wolf axes. We use KT to show with if the maximum density defined as we take the max over all the convex sets. The density is less than. So I use the word this notation less approximate than 1 means less than equal than something like some epsilon. That's a very small positive. So now let's with this definition,
Can I ask you a stupid question? I don't understand the definition of density because you're dividing the volume of the union of the tubes by the volume of the set.
no, so this one is the number of tubes contained in that. That's the notation. So
Okay, so it's a cardinal. So yeah, the meaning of the double bars is
maybe,
changes from one thing to
yeah, maybe I should just use this one. I was debating, do you think this is a better notation?
Okay, that is now I understand.
Okay. Yes, maybe, yeah, maybe this is good. So yeah, so the density of tubes is that has nothing to do with the volume and with volume of unit of tubes yet. So our whole idea is trying to relate this term with the lower bound no volume. So this definition does not have a volume. It only counts the cardinality. But as we saw from the enemy example, this is like a necessary condition because otherwise, there is no hope that the inequality is true. At least with inside of the. So let me first make a second definition that's sort of like a dual to the first one, but for most of the time we'll be working on the first definitions. So P that is Boltzmann by convex for this means in W. So W is any convex set. For example, we can take W to be the unit ball. So if T satisfies convex wolf axioms in W, if for any other convex set V contained in W, the density of tubes in V is less approximate than the density of tubes in W. So these two definitions are somewhat dual or complement to each other in a following sense. The first definition of the Castile convex wall vacuum just says that the density of tubes is less approximate than 1 inside any convex set. The density is small. And the second one says that, okay, the density of tubes is maximum, is like for any convex set containing W, the density of tubes is maximized by the density of tubes in W. Usually we think about such set as, let's say T is a set of tubes containing W, that the maximum density is attained by W itself, the convex set that contains it. Now let's, this is the main definition of the lecture series. Let's try to digest it. First of all, let's try to compare it to this Kakeya assumption. So previously we said that this Kakeya conjecture is about, here is the assumption about a set of tubes, and we hope that it gives us good lower bound on the volume of unit tubes. So maybe, so what does this say? The Kakeya assumption just implies that the number of such tubes is approximately delta to the minus n minus 1. And once we know that, then this lower bound just corresponds to this bound, because this is 1 and this is 1 for that for a set of tubes satisfying the Kakeya assumption. And now we have 3 assumptions, 1, 2, and 3. How are they related to each other? So this Kakeya assumption, this assumption implies both the Castile Wolf axioms, convex Wolf axioms, and the Frostman convex Wolf axioms. Why this is true? And so let's just focus on before I said anything, a convex set by the Jones ellipsoid theorem is this convex set is any convex set is approximately up to some doubling constant depending on the dimension is approximately an ellipsoid, and an ellipsoid up to some like doubling is approximately a rectangular box. So even though we say convex set, we should try to imagine this as some sort of rectangular boxes. Now let's just work on 3-dimensional. Let's say W is an A times B times 1 box. And then suppose a set of tubes satisfies the Kakeya assumption, then what is the number of tubes contained in W now is less than the volume of W divided by the volume of T, because this has side length B and A and 1. The set of directions that we can put a delta tube in W corresponds to roughly A times B rectangle on the sphere. So the direction of the delta tube corresponds to a delta cap on the sphere, and so the number of, since we only have 1 tube in each direction, then the number of tubes in delta separated direction we can put in W is as most the volume of W divided by the volume of 1 tube. And so this is equivalent as to the density of tubes is bounded by 1. And that is why this Kakeya assumption on a set of tubes implies the Kastel convex Wolf axiom. On the other hand, since and the Frostman-Wolf axiom in the unit. On the other hand, since this implies that the number of tubes is roughly delta to the minus n-1, we know that the density of such tubes contained in the unit ball is roughly 1. So we can just put this term on the right-hand side, and it implies that the set of tubes satisfies the Frostman convex Wolf axioms in the unit ball. In other words, since this Kake's assumption is stronger than the Kastel convex Wolf axioms and also the Frostman convex Wolf axioms in the unit ball, so if we can prove that if we can prove good volume lower bound on the set of tubes satisfying those assumptions, then it implies nice bound on the size of the Kake set. And since here we said that this Kake assumption implies the number of tubes is roughly delta to the minus n-1. So using those assumptions, this also shows that the number of tubes is less than delta. And this one shows that the number of tubes is greater than the volume W divided by the volume T. How does this work? For the first bound, we can take W to be the unit ball, since the tubes are contained in the unit ball. Then the density of tubes in the unit ball is less approximate than 1, implies that the number of tubes is less approximate than delta to the minus n-1. And for the second term, we can take V to be 1 delta tube in it. So the density of tubes in itself in one of the delta tube is 1. And then this implies that the number of tubes is at least the volume of W divided by volume T. So that is why we say that the two definitions are kind of dual to each other, because one gives the cardinality upper bound, and the other one gives a cardinality lower bound. And for the Kake assumption, it's approximate. And let's continue to digest this definition. Here are more examples. Of tubes satisfying both Kastel assumption and the Frostman-Wolf axioms in the unit ball.
Excuse me. You wrote the cardinality of the set. You mean again up to some delta minus epsilon?
So
in the first implication about.
For this one, if we say that the density of tubes is less approximate than 1, yes, it's up to delta to the minus epsilon. So this one also. But for the Kake assumption, and this is just some constant missing number, and is stronger than less approximate than delta epsilon, minus epsilon. Are there any more questions? So we have seen that a set of tubes satisfying the Kake assumption implies both the Kastel and Frostman convex Wolf axioms in the unit ball. We are going to see some simpler examples that for those examples, sometimes you can see this bond immediately. It's not as hard as the packet set. First example is, let's take one direction. And then we take a set of tubes to be all distinct delta tubes in direction theta. And if we take T to be all distinct delta tubes in direction theta, then the number of tubes is like delta to the minus n minus 1. And since they are all parallel, it's like they basically retire roughly the unit ball with those delta tubes. So it's really easy to compute it. So for the first example, we can just say the bond is 2. And the second example is we just randomly choose let's say delta to the minus n minus 1, many delta tubes. So we choose the tubes uniformly at random. And for this example, it's also not hard to show that with high probability, this bond is true. And then this is a more restricted assumption, and it's much more difficult to prove. Another remark is following. This is something that about this definition that we are going to use over and over. It's a simple observation. If T prime, if we have a subset of our original set of tubes, and the set of tubes satisfies the convex wolf axioms, then T prime is also satisfies the convex wolf axioms, because it's a subset of original tubes, so the density of T prime in any convex set is less or equal than the density of T in any convex set. So this is an easy observation, but also useful. Now we are ready to state our main theorem.
You are saying the example number 2 is kind of easy.
Yeah, if we choose a tube like uniformly random, and then we choose this many independent yes, we choose this many, and it's not hard to show that with high probability the delta to the minus 1 tubes we choose, the union of them has volume approximately that one. So the theorem, the two-dimensional case was basically an argument of photobus in the 70s. And the three-dimensional case is Josh. Says that, well, it's not very hard to guess the thing. If a set of, so now still T is a set of delta tubes contained in the unit form in Rn. If the set of tubes satisfies the Kasta-Wolf axiom, then the Kasta-convex Wolf axioms, then we expect them to be essentially disjoint. The union of tubes has volume greater approximate than number of tubes times the volume of one tube. Here again, I absorb those delta to the epsilon powers. And the second thing is, if a set of tubes satisfies the Frost-Lang convex Wolf axiom in some convex set W, then the unit of tubes in W is roughly approximately again up to delta to the epsilon, the volume of W. Maybe. So this corresponds to our heuristic here, because the first Castel convex Wolf axiom assumption says that the tubes has a low density small density in any convex set. So we kind of expect them to be essentially disjoint. And the second definition says that if a set of tubes satisfy the Frostman convex Wolf, use this notation F. Satisfy the Frostman convex Wolf axioms, then the maximal density is attained by W, so we expect the tubes to fill out W. Are there any questions about the statement of the theory? And also, observation is that it suffices to prove for W equals to the unit cube, because we can rescale this convex set to roughly the unit cube, and then we can decompose them into tubes, so that as long as we prove the version for the unit cube, then we can easily deduce the version for the tubes contained in any convex set. Good. Apply rescaling. And decompose. So, for today, we are going to use a simple L2 argument to prove this two-dimensional case. We are going to introduce the Cordoba argument, and this is also a way for us to digest this definition and see how it's used. This two-dimensional Cordoba argument will also be used over and over again in the three-dimensional case as well. So we take the indicator function of a tube, and we can sum over T contained inside our collection of tubes. Then this integral will give us the number of tubes times the volume of one tube. And this function is supported on the union of tubes. So the support is here. And then we are going to use Cauchy-Schwarz. So I'm going to square everything. It's bounded by the volume of union of tubes times the integration of the square of the function. So we know this term. That's just the cardinality of the tubes times the volume of one tube. And we want to give a lower bound on the volume of unit of tubes. So it suffices to obtain an upper bound on the integral of the square of the sum of indicated function of tubes. And this term, we can write it as sum over T1 and T2 in our collection of tubes, and then calculate the volume of their intersection. And how do we estimate that? So fix T1. Then we only need to sum over T2 in T. And we can again dyadic decomposition sum over rho between delta and 1 dyadic. And then sum over the T2 in T such that the angle between T1 and T2 is roughly low. Since here we only have dyadic many terms, so it's like log 1 over log delta many, absolute value of log delta many terms. And now, how do we estimate this one? Since we have fixed, know roughly the angle, then if we have T1 here, we're only interested, so T1 is fixed, and we are interested in T2 in those T2 that intersect T1 and has angle of roughly rho. So this is T2. And we know that their intersection is approximately a segment, is contained in approximately a segment of length delta over. So this angle is roughly rho. Then this term is bounded by so now since we have fixed T1 and T2 that intersect T1 with the angle rho, approximately rho is contained in this is contained in the rho neighborhood of T1. So this term is bounded by the number of tubes contained in the rho neighborhood of T1 times the volume of this segment, their intersection, which is delta over rho times delta to the n-1. And how are we going to use the two assumptions is just to bound this term. Those Castile convex wolf axioms or the Frostman convex wolf axioms will give us some upper bound on the number of tubes contained in the rho neighborhood of T1. This is just one rho tube. And this term is let's read it. It's less approximate than so the volume of rho neighborhood T1 is just rho to the n-1 divided by delta to this. So this is the volume of one tube. If it's the set of tubes satisfies the Castile convex wolf axiom, and it's bounded approximate than rho to the n minus 1 times the total number of tubes if a set of tubes satisfying the Grossman-Fock maximum condition. So the different assumption gives a different upper bound. And once we plug in this upper bound and plug in here and use the fact that there are only log delta, absolute value of log delta many terms, and then plug it here, the just calculation will give us the corresponding bound for the two-dimensional case. Yeah, so the two-dimensional case is basically Cauchy-Schwarz plus dyadic decomposition and plus application of the assumption. Are there any questions? So now let's pause and analyze the proof. So first of all, where does it use for n equals to 2? Like why this does not hold when n is larger? Let's just try to trace back the calculation for this for the first case. Let's plug in and so if we plug in, then it gives us for this is less approximate than log delta times rho times to the rho n minus 2 and then times delta, and we plug in here. Since this term we also need to sum over the number of tubes. So this one is less the number of T1. So for the first assumption, this is bounded by the number of T1 is less number of tubes times. So I absorb this log delta into this lesser approximate times rho to the n minus 2. And now if we go back, this equals to number of tubes. Okay, I'm just separating the square into writing this one and the volume of tubes is roughly n to the minus 1. So let's compare. We want to bound, we want the lower bound on that. Then this gives us it's greater approximate than and the rho could be as large as 1. So the worst case is when rho equals to 1. And then this whole term is 1 when n is 2. And this is much smaller than 1 when n is greater than 2. So that's just from the calculation that yes, this proof doesn't work for higher dimensional n. But fundamentally, what was not efficient in this argument. The part that's not efficient is the follows. So here, since we said that the worst case is when rho is roughly 1. So in the plane, if we have two tubes that has angle roughly 1, and they are all contained in the unit bits, if they have angle roughly 1 and they contain a unit disk, then like they almost surely should, when I say almost surely, that like you can see that most pairs that they intersect. That's what happens in the plane. So when the rho equals to 1 case, this calculation is not that lossy. But when n is larger, higher, like in 3-dimensional space, even if we know that two tubes has angle approximately 1, they have a lot of space to go around each other. They don't intersect at all. And so when we want to have a good estimate, we somehow need to take that into account. But through this simple upper bound, like the intersection T1 intersect T2 has volume bounded by this segment. For those that are intersecting, then this is sharp. But there are a lot of them, they don't intersect, so this term should be 0, but we don't know how to take that into account. And so like somehow we have to control them, but we don't know how to do it. And that's the one of the difficulty in 3-dimensional space. So what do we know in 3-dimensional space? First of all, are there any questions? So the 3-dimensional case, as we said before, the issue is T1 intersect T2 is empty for most pairs. But if we just look at those pairs that they intersect, so this is actually Wolf's idea. So he looked at a fixed tube, that's the T1, and all the tubes that intersect T2, T1, all the T2 that intersect T1. So if we look at just this object, this is called a hairbrush. And then if we focus on all the tubes that intersect the fixed tube, this focus on this hairbrush, indeed we could get some meaningful lower bound, and that is a set of tubes satisfies both the test type and convex and cross-band convex. So this in particular implies the number of tubes is roughly delta to the minus the -2 in 3-dimensional space. So we focus on 3-dimensional space, 3-dimensional case right now. Then the union of tubes has volume greater approximate than delta to the 1/2. So, and this is the bound that if we just take into account all the tubes that intersect one fixed tube, and we get that also by some Cauchy-Schwarz bound. But this has to be smarter than the one we have seen before. You need to use some double counting and Cauchy-Schwarz. This bound, even though it looks the argument is quite elementary and not too long, but this bound turns out to be very hard to improve. So for like 30 years, there was only epsilon improvement of this bound. And even the epsilon improvement takes a very long paper, several very long papers. So the first attempt, the Cass-Labat and in Cass-Labat in the year 2000, they managed to improve this 1/2 by epsilon. In fact, it's not even this bound. It's like after some thickening, and this holds at that scale. And they managed to get an epsilon improvement. And what's more more important is that they figure out why this bound is very hard to improve. They found some example called so-called Heisenberg group example in C3. But for simplicity, I'm going to present a slightly different example that's simpler to calculate. So the example is, let's see. C1, C2, C3 in C3 that satisfies this projective equation. We want to show that this example contains a lot of complex lines. So imagine in a world that we don't really know how to distinguish C and R. We only look at three-dimensional space. Then the analog of a line is going to be a complex line. And then how do we see how many complex lines are there contained in this cube? So through the point 1, 0, 0 is contained in cube. So through this cube, through this point 1, 0, 0, cube contains a cone. This is a key. And this cone is this is our C2. C3 for theta. And every theta determines a complex line here. So this is the L theta is parameterized by 1, not 1. Yes, it's parameterized by this 1 and theta z and z. And this cube contains one real dimensional set of complex lines. Because the set of theta, so the theta that L theta contains in this cube has to have a normal 1. So it's like half dimensional C's. On real dimensional set of complex lines. And so in total, Q contains 4 real dimensional set of complex lines. By double counting, because now Q has a dimension. Q has real dimension 5. And since it has real dimension 5, and each complex line itself contains a 2 real dimension set of points, and through this Q, so we're just taking 1 point, but it's the same that for any other point, Q also contains a cone of complex lines. So by double counting, this Q contains like 5 plus 1 minus 2. It contains 4 real dimensional set of complex lines. And 4 real dimensional set of complex lines is, if we divide by 2, is like 2 complex dimensional set of lines. And this corresponds to the fact that corresponds to that in R3 we have a 2-dimensional set of directions or 2-dimensional set of lines. So this example gives a sharp bound for that when if suppose we do not know that the space is R3, but suppose we only know the suppose we don't care about which space we are in. And so and we can do it similarly, like taking the, let's say, delta neighborhood Q, and each complex line, we can take a delta neighborhood and then make it like delta complex Q, the tubes. And this example will satisfy both the Kestel convex Wolf axioms and Frostman convex Wolf axioms. But then the convex set we are going to also define over C. So to summarize, this example gives a short bound for that if we don't know which space we are in.
Yeah, but what is the relation between the two pictures?
Sorry?
I mean, the two pictures look very different.
Oh, sorry. This picture is the proof strategy of Wolf. So this same strategy actually also works in complex space. And this picture is just to illustrate why it contains a one-dimensional set of complex lines. This picture is just to explain this example. And this picture is about the proof strategy. And also, yeah, as Wolf's proof is very general, it works both in R and C. So, and since then, imagine we want to improve Wolf's bound, then we have to somehow distinguish this example and the object that we work on. So there are a couple of ways to distinguish that. One thing is that in the set of the tubes that we are interested in are containing Rn. So we want to say that in fact our tubes lives in R3, but the example that Kestel et al. Discovered lives in C3. So we need to use that. Or previously, people also tried to use the Kaké assumption. At least that was also what Kestel et al. Did. They don't work with this Kestel Wolf axiom or Frostman Wolf axiom. They work with the original Kaké assumption and say that the set of tubes has to contain one delta tube in every delta separated direction. But for this example, one can check that it does not contain all the directions. So that's the approach they used. But I think at the beginning it's more natural to try to use the Kaké set assumption because that's the original question we are interested in, and also it's not that obvious. How do we distinguish R3 and C3? How do we know which space we're in the actual tool? But later, as it turns out that when we want to do inductional scales, the Kaké assumption is very hard to use. It's very hard to use the assumption that it contains a delta tube in every separate delta separated direction, because once we zoom in or thicken the tubes, this assumption fails. So the approach that we used, and also that's also people who have been trying for many years, is to in fact use the assumption that our set of tubes are containing R3 and try to distinguish R3 and C3. And in fact, there are many other problems that also has the same flavor. So a lot of other problems in projection theory, in geometric measure theory, has the flavor that the theorem we want to prove or the problem we want to work on will fail for some examples in C, but we really want them to hold in R. And so people have been trying very hard to develop tools that would distinguish R and C quantitatively. And that is let me just give a very short introduction to projection theory, because in projection theory, there are a family of some other problems that also have the same issue, and that's in those relatively simpler problems, that's where people have developed tools to distinguish RNC. And even also in the proof of the Picasset conjecture in R3, we also need to borrow tools from projection theory that have this property that is able to distinguish these two examples. So the projection theory studies the following. Let's say we have a Borel set in Rn, and we have a collection of m-dimensional subspaces. And for any subspace, I use V again to the subspace. We use the projection PV. It's just the orthogonal projection. And we are interested in the following. Can we find a subspace in our collection such that the Hausdorff dimension of the projection image is large? So in fact, one can also, let me just say that there is this classical result of Mastrom and Matila. So Mastrom proved it, I think, in 1953, and Matila generalized that in higher dimension in the 70s. So for almost every V, the Hausdorff dimension of the orthogonal projection is equal to the minimum of the Hausdorff dimension of the E. So for almost every m-dimensional subspace, the orthogonal projection preserves the dimension or has the maximum dimension. But this gives the sharp result for almost every m-dimensional subspace. But the difficulty is when lambda is much smaller. Let's say for example, lambda is a curve. In fact, the Takea set conjecture could be rephrased as such a problem when lambda is a curve in higher dimensional space, when n and m are larger. And as I said, this problem that we can ask different things. For example, for different set of lambda, there are and also for which set of E, we have good projection bound. So if also we can choose different M and N. So even though this is like a simple question, but sometimes people want to know for which M and N and for which lambda, for which E, we have good estimate. And those more specific questions are much harder. And different versions of that will have some versions that will face the same difficulty in the sense that something is true in Rn, but not true in Cn. And as people study those questions, people developed some general scheme in the recent years. That is, we first study a sticky case. That's a special case of the problem. That has a property that the problem behaves roughly the same at all scales. And then once we are able to solve the sticky case, then we use this as some induction base case to prove for our general sets. Let's say general Borel sets or general. And this approach was successful in several of the problems and in projection theory. And this is also the approach that we are like this very general approach that we adapt to work on the Kakeya set problem in R3. I just want to give a very short introduction that put into context. So this general approach already happened for other problems in projection theory. Now, what is the sticky case for the Kakeya set problem? So this sticky case has similar property at all scales. So even to figure out what is the definition of sticky case is not obvious. So the word sticky was also introduced in this paper of Kaslava and Tao. In their work, they show that if a Kakeya set was to saturate this bond, then the set itself has to be sticky, braining, and planing. The stickiness in their definition is the follows. For them, they work on with a set of tubes that consists of one delta tube in every direction. And for them, the stickiness means that the tubes has a nearby direction. They should also close to each other, like stick to each other. For example, if the tubes that has close direction, they are like apart, have a large distance, and this is not sticky. So sticky for them really means that tubes, this small angle stick together. But for us, we need a slightly more general notion of stickiness that's adapted to this Katz-Tau convex wolf axioms. So next, I'm going to present what it means for the sticky case for our setting. So again, blackboard T is a set of delta tubes containing a unit ball inside Rn. We say that a set of tubes is sticky if for any row between delta and 1, T row, the T row is the collection of row tubes covering delta tube, set of delta tubes. Satisfies the Katz-Tau convex wolf axioms. Okay, now we are going to explain what is T row and also what's the consequence of the stickiness property. So first of all, during the proof, we have to use a lot of pigeonholing. So at the beginning, I'm going to talk about some pigeonholing in detail, but later we are going to omit all the pigeonholing so that when people are getting more comfortable. So the first pigeonholing is following. So one can, and I'm using pigeonholing to explain what's the role here. So we can find, for any set of tubes, we can find a subset, a significant subset. So up to some 1 over absolute level of log delta, such that T prime is a disjoint union of the tubes contained in T row. And for any T row, is roughly the same. Means that we can organize our data tubes to be contained in a collection of row tubes. So for any row, we just sort those T row according to the number of data tubes contained in it, and then we find a popular number, and then we throw everything out. So this is just pigeonholing. And so for the rest of the lectures, we are going to assume our tubes are already pigeonholed. Means that this holds for every row between delta and 1, and for and then we assume that we are in the regime of T prime. So in this sense, the set of T row behaves containing a set of data tube behaves very well in the sense that each T row will contain approximately the same number of delta tubes. And this set of T row satisfies the Castel convex Wolf axiom, means that the row tubes, those row tubes in T row do have a density bounded approximate than 1 in every convex set. And there are a few consequences. So as before, we said that the sticky case will have similar properties at all scales. So this implies already T row itself is satisfied by the Castel-Wolf axiom. Means that the thickening of those yellow tubes will satisfy the Castel convex Wolf axiom. And also, we previously said that if we have a subset of the tubes, it should also satisfy the convex Wolf axiom. So this means that if we zoom in, like we look at the data tubes contained in one row tube, it should also satisfy the Castel convex Wolf axiom. By the way, when we take rho equals to delta, then these two are the same. So T is also a Castel convex Wolf axiom. And this also means that the number of row tubes is less than rho to the minus 2 because of Castel convex Wolf axiom. So this sticky property is preserved under thickening and also restricting. So in fact, it even implies the T is sticky. Even implies that T row is sticky. And rescaled T containing T row is sticky. Okay. So what we proved is we first proved that if a set of tubes is sticky in R3, then we have the desired, then the tubes are essentially disjoint. The unit of tubes has volume greater approximate than the number of tubes times the volume of one tube. And this is based on a blog post of Terry Tao on the argument of Katz and Tao in 2014, when they have thought a lot about how to prove the Katz-Kassett conjecture in R3, and they put their approach on the blog post. So the stickiness, is mostly based on that. And if it's sticky free, then so based on it. That's and this theorem, so before I finish this, the example here is sticky. So this theorem already has distinguished this bad example in C3 and the set that we're interested in R3. And so it uses a lot of projection theory that distinguishes C and R. and we are going to see some ideas of how to prove this theorem in the next lecture. Also, the general strategy is we first prove the sticky case, and then the last lecture we are going to see how the sticky case implies the general case. So it implies when the set of tubes itself is satisfied the Kast-Wolff axiom, we have the same bound. I will stop here. Thank you.
Thank you. Are there questions? The online audience can also ask questions if you want. You can just unmute yourself and just ask the question. Please.
In the general picture of the Kakaya set conjecture, so you want to find some lower bounds that are as sharp as possible.
Yeah.
I wonder if re-expressing the conjecture in some kind of probabilistic setting, you may improve significantly the lower bounds.
You mean the current lower bound?
Yeah.
In what do you mean in probabilistic setting?
This I don't know.
Generically, the lower bound will be there.
Maybe not with a uniform measure, probably not, but maybe Gaussian measures. And I don't know. Has it been explored or not?
I'm not sure, but I think like if we choose uniform at random, it's also not hard to prove the best possible lower bound.
Yeah, this is why I'm speaking maybe about the Gaussian measure.
Yeah, I'm not sure Gaussian measure is that different from uniform measure. If we are happy to use some constant like delta to the minus epsilon.
What are some easy corollaries of this for solutions of the Schrödinger equation? I mean, how can you use all of this theory for applications to PDEs, for instance?
That's a good question. I don't know enough Schrödinger equation to know that, but I should motivate people by saying that Kakaya conjecture, set conjecture is closely related to the Stein's restriction conjecture, which is about LP norm of a linear solution to the Schrödinger equation, and using some knowledge of the Kakaya set, one could potentially improve the restriction estimate. And I don't really know how to go from restriction estimate to probability about Schrödinger equation. Also, actually, in the colloquial talk, I'm going to present like how to use those not exactly Kakaya that estimate, but some closely related estimate to improve the current vector, the restriction estimates in R3. So I hope I could explain more in the colloquial.
Yeah, but then, do you think that the higher dimension is very far from?
I don't know, because remember the enemy example I presented here that involves some projects, and the fact that we have to deal with some curved object will increase a lot of the difficulty. And actually, we can see that when we go through the proof, which step will fail if the convex set is replaced by, let's say, project. There are some steps will fail, and yes, that's the key difficulty in higher dimensions.
Yeah, but then I am puzzled with that example, because that example, one of the complex lines, I mean, how many more animals like that one can you find in higher dimensions?
Yeah, there are a lot more enemies, exactly, about something like that, and also something, just the project in R4 is already an enemy example. One has to rule it out. Yeah, so far, all the enemy examples that we have found are like algebraic. So it's natural to guess if we rule out the algebraic enemy examples, it might be okay, but there's no proof saying that they are the only enemy examples.
So the next lecture will be on Wednesday,